My name is Luisa Rebull. I'm an associate research astronomer at Caltech IPAC. IPAC is the home for many different archives that relate to NASA data. So the archive I work for is called IRSA, the Infrared Science Archive, and it's the long-term repository for all sorts of NASA long wavelength data, including that from the Spitzer Space Telescope. Part of my job is actually to do science, by which I mean I take data, I write proposals, I write papers, I reduce data, I try to figure out what it means, I go to conferences, I go on observing runs, all those things go into being an astronomer. But also, as part of my job, I work for IRSA, the Infrared Science Archive, which is NASA's repository for all sorts of long wavelength astronomy data. So I help with the archives. I help design the interface. I help make sure that the data are easy to use and has lots of good instructions so that astronomers coming after us will still be able to learn things from the data. Turns out these data are very, very rich. The very first all-sky infrared survey was called IRAS, and it went in the 80s. We are still learning things from IRAS data, and IRAS data also lives at IRSA, where I work. So we're running towards petabytes of data. There's so much data and so many things that you can do with it, and part of my job is to make sure that everyone can access it, whether we're talking a summer student embarking on her very first research project ever to an emeritus professor who can barely read his email. Everyone in between needs to be able to get access to those data. And so we have to make an interface that works for all of those people in order to get science out of the archive. It turns out I have always wanted to be an astronomer ever since I was very little. I was the only little girl in kindergarten who did not bring a doll to the post-Christmas show and tell. I brought my motorized Legos, which I had not put down since I got them. Apparently I'd gotten dolls, but they were still in their packaging. I really wasn't very interested in them. So I've always wanted to be an astronomer. I fell off the wagon for a while in middle school in particular, but also late elementary school, because I somehow, despite my parents' best efforts, bought into the idea that girls can't do math. And so I didn't know how I was going to make that work. I really wanted to be an astronomer, but I didn't understand that, of course, girls can do math. And moreover, math when you're in 5th grade is really just addition, subtraction, multiplication, division. It's really boring. I'm sorry, but it's true. It's really boring. Real math is so much richer than that, so much more interesting, so many more fabulous things that you can do with it. And once I got over that hump and got to college, I was still uncertain that I could do the math. So I went to college thinking, okay, I'm going to try to major in physics, but I'm always going to have a backup plan. And I realized by like the second semester of my freshman year, when the chemistry department chair was trying to recruit me away from physics, that maybe I was doing okay. Maybe I could handle the math. And so when I was in college, math really was a tool to be gotten through as quickly as possible so that you could get to the physics. And when I went to graduate school in astronomy and astrophysics, physics was a tool to be gotten through as quickly as possible so that you could get to the astrophysics. And so there was a lot of learning that had to happen in a very short amount of time. But I went to the College of William and Mary in Virginia for my undergraduate degree in physics, and I went to the University of Chicago for graduate school. So when Spitzer was first launched, there were lots of things that made it innovative. One of the really amazing engineering changes that were made that enabled actually Spitzer to survive as a mission was the first mission design, or one of the early mission designs, had the entire telescope inside basically a fancy thermos bottle so that the whole telescope would stay cold. But that meant for an 85 centimeter telescope, you had to have a really big spacecraft because it had to have all the infrastructure for keeping that cold, and testing it is really hard because you have to cool it down and then test it, and then something goes wrong, you have to warm it up, then you have to cool it. So it takes a really long time. The development phase is very long. But the revolution in engineering that was brought is you have the same size telescope, so the same light collecting power, but now all of the cryogen, all the thermos bottle is actually outside and it just exhausts past the telescope. And so by designing the spacecraft very cleverly to keep track of all the thermodynamics and let it passively cool off into space, helped by little puffs of cryogen, meant that we were much smaller and much less expensive to test and develop, and we could go in a much smaller rocket. So those innovations enabled Spitzer to survive several really bad budget cuts that were going on at the time. So that was one major innovation. The next major innovation is the orbit that it's in. So most people, when they probably think of an orbit, they probably think of something in what people call low Earth orbit. In other words, it goes around in about 90 minutes. It can be near the equator, or it can be something that goes around from pole to pole. But those orbits are usually only about 90 minutes, and they're very short. And when you're in those orbits, you're so close to the Earth that you have to spend a lot of time not looking at the Earth. And the Earth is very warm. So if you're observing in infrared, which you can think of as little bits of heat, your spacecraft has to be cold. So by Spitzer's orbit Spitzer is not in Earth orbit. Spitzer is in an Earth trailing orbit. It orbits the sun just like the Earth does. And so by getting away from the Earth-Moon system, it can cool off very effectively. And we can spend most of our time doing science because we don't have to spend a significant amount of time not looking at the Earth. And by being able to get away from the Earth-Moon system, we can passively cool and stay pretty cold just by passively cooling. So infrared light, the way that you encounter it every day, is as heat. So the things that heat up in your toaster that sort of start glowing a dusky red and then become brighter red and then maybe orange, and if you've turned it up to broil, maybe yellow, those things are glowing, and you can see some of the light in the optical, but most of that energy is coming out in the infrared, which is what you want in a toaster because you want it to toast your bread. But when there's all sorts of other things that emit infrared too. You emit infrared. And the reason why people want to change lights from incandescence to fluorescence is that incandescent lights are a filament, just like in your toaster, that heats up. And in order to get it to be bright in the optical, you're actually wasting a lot of energy in heat. And so by switching to LEDs or fluorescent lights, you're not emitting all of that stuff in infrared. But the infrared is all around us. Your remote control works with infrared light. But when you're going to space, you want to measure little tiny bits of heat. And so it really is very helpful to get away from the Earth because the Earth is warm. I like having the Earth warm. It allows us to live here. But when you're trying to do infrared astronomy from the ground, it's really hard. You have to get to a very high, very dry place. And even then, the best analogy I can think of for observing in the infrared from the ground is using a telescope in the optical that's made out of those fluorescent light tubes, because in the infrared, your telescope is glowing, even if you're on a very high, very dry mountain. And so by getting out into space, you're more sensitive to little tiny bits of heat. The other really important thing that you have to remember when you're observing in the infrared is that infrared light, for the most part, does not make it down to the ground. There are some absorption lines in the near infrared where, again, I like having oxygen and water and even carbon dioxide because the plants need it, but they take bites out of the spectrum. And so if you're in the near infrared and you're very high, very dry place, you can do some infrared astronomy. But for most infrared astronomy, you really do need to get out into space because it's cold and because the infrared doesn't make it through the atmosphere. Spitzer has done a lot of really amazing things, but because I study stars, my world is kind of focused on stars and planets. So there's lots of cool things that it's done. So you know that Saturn, we think of Saturn as the ringed planet. It turns out Spitzer's discovered a much larger ring around Saturn. It's very tenuous, so tenuous that if you were standing in the middle of it, you might not realize that you were standing in the middle of it. But it is actually probably populated by dust off of one of Saturn's moons called Phoebe. And there's another moon called Iapetus that for a long time people didn't understand what was going on because half of Iapetus is black and half is white. But it's because, much like your car driving through bugs, all of the bugs end up on your windshield, not on your back windshield. When you have Iapetus, the black side is plowing through that dust ring, leaving the back of it a brighter color. And people thought there must be a ring, but Spitzer was one of the ones Spitzer was what found it. What else? So I study star formation. I study how stars form, stars like our sun form. And Spitzer has really revolutionized our understanding. It used to be that there were not very many young stars known, and Spitzer's found hundreds upon hundreds at all phases of life. So we now have a much better understanding of how stars like our sun form and the timescales on which it must work. Also, what Spitzer is really known for is following up exoplanets. So there's lots of missions that are out, either ground-based or space-based, looking for planets. Spitzer doesn't look for planets, but it's really good at following them up. So when you think of some of the really famous planet-finding missions like Kepler, you've got the star and the planet, and Kepler is looking in the optical for little tiny dips as the planet moves in front of the star. Spitzer, especially if the star is young and the planet is young and gassy, it's actually seeing tiny dips in light when the planet goes behind the star, because we're looking in infrared and the planet is bright in infrared. And so when the planet's in front, you're seeing light from the planet and the star combined. But when the planet goes behind, the star is blocking the infrared from the planet. And so we're seeing photons from the planet itself, which is so cool. It was the first time anybody had done that. There were lots of observations from which we inferred planets, but none in which we were sure we were actually seeing photons from the planet itself, which is really cool. And then there's a star system called TRAPPIST-1, which has a huge number of planets around it, and it's a very low mass star. It's an M star, which means it's a fraction of the mass of our sun, but it has planets around it in many, many planets around it. And Spitzer was helping us understand how many planets there were, because before Spitzer observations, I thought maybe 2 or 3, and now we know there's 7. So is there 7? Maybe there's 8. I think there's 7. Yeah, so now we know there's 7. And it's because of Spitzer that we know that there's 7. And because of the observations that Spitzer was able to do, we can interpret the transits that we're observing with Spitzer and with ground-based missions, ground-based surveys. Asteroids are nature's way of asking, how's that space program coming, right? So rocks are out there. There are a lot of rocks. Some of them are very big. They're very hard to find in the optical, but in the infrared, they glow. So it's really, really important that we keep these infrared missions going so that we know where the rocks are, because I would like to know where the rocks are before they hit us, not on their way into the atmosphere. So for the average person, that's probably the most important connection they might need to make, because planetary survival depends on it. So I study star formation, but I also study how stars rotate. And so anybody who's done any kind of skating, whether on ice or on roller skates, knows that, or even if you just watch the Olympics, when a skater pulls in her arms, she spins faster and faster and faster. So when you start with a big cloud of gas and dust out of which you're going to form stars, you're starting big and you're going to end up small. So the logic would say that all young stars should be spinning so fast that you might not even think they could form. They might be ripping themselves apart. They're rotating so fast. Turns out, of course, stars do form because we're here. And so that angular momentum, all that spin has to go somewhere. And all of that is tied into the magnetic field of the young stars and how it's interacting with the matter around it, because it turns out that stuff doesn't just fall radially into the star. It falls onto a disk first and then spirals in. So it's all sorts of complicated stuff that's bound up in magnetic fields and planet formation, all coming back to where's the spin going? You start big, you end up small. Where's all that rotation going? And planet formation might be really important. So in terms of a easily accessible hook, certainly a skater spinning is probably the most easy way to explain that. But that's a lot of what I do, is understanding how stars' rotation rate changes over time and what implications that has for stellar evolution, planet formation, all sorts of good things. The program that I run now is called NITARP, the NASA IPAC Teacher Archive Research Program. And we partner small groups of educators with a research astronomer for a year-long research project. And we mostly use Spitzer data, although the unifying theme for all of these NITARP projects involves data that's housed at IPAC. Fortunately, that's really easy, because something like 1/4 of all research journal articles in the world right now use data that originally came from IPAC. So it's really easy to get lots of science out of the data at IPAC.